Well, hello friends. Welcome back to the program. Today we're going to look at some JavaScript optimization because I kind of overheard a conversation on Discord the other day where people were trying to benchmark something in lib.js, and then it turned out that the loop around the thing they were trying to benchmark was hogging all the CPU time, and that's a pretty sad thing when that happens. So I thought today we're going to try to optimize this type of loop a little bit. So it looked, I guess, let's say a million even. It looked a bit something like this. And then they had something interesting inside here. I'm just going to evaluate I just so we do something. And then this was sort of what their test looked like. And if we time that, we can see that it takes 0.88 seconds. Which, you know, it's quite a bit of time for just an empty loop like that. And lib.js is rather unoptimized engine, of course, but there tends to be a lot of low-hanging fruit, and I'm pretty confident that there are low-hanging fruit here. So today the mission is to cut this down, see how much we can cut it off of it, but it would be cool to get it down to like half a second or something like that. So the first thing we're going to do is generate a call graph profile with call grind so we can see what the program is doing and where the time is disappearing. And actually, let me make the test a little bit shorter. I'll just cut off one of these zeros just to make Valgrind crunch through it faster, because Valgrind does a full CPU instrumentation run of the thing, so it can be pretty slow if you have long running programs. But this is better. So let's open that up in kcachegrind and take a look. So on the left here, we can see that 97% of runtime is within for statement. And if we switch to the self view, we can see that we have a lot of shape lookups being called by storage set and storage get. Storage get is totally dominating here, 91%, 92% of calls. And then we have, so like it's basically like property access. So the thing to know about a program like this is that this is actually a global variable. Because it doesn't belong in a declarative environment as its lexical scope, but rather it belongs in the global environment here. If I were to wrap this in a block like this and maybe even make it a let, then it would no longer be a global variable. And if it were not a global variable, actually, let me put back this zero that I got rid of. If it were not a global variable, then it should run a lot faster. So yeah, 0.25 seconds instead of 0.8 whatever. 0.88. Actually, maybe I don't even need those braces. Yeah, so var versus let makes a huge difference here. And the reason is when you use var here in this context, where you're not inside of a function, you're just in the free global context. So var means that it ends up in the current variable scope, which is the global environment. And when you store something in the global environment, it ends up in this object called the global object. So we can actually access global variables as I, like this, right? So if I log this at the end, then we can see that it prints out 1 million. Because even though this looks like it will be similar to let like this, they are quite different. So let does not put I into the global object. It just exists in the local declarative environment, but this fella is a field in the global object, so, or a property in the global object, I should say. So Why is this an issue? Well, the issue is that declarative environments, like function environments and block scope environments, we already optimized those. But for global environments, we don't do anything. So if we look at, let's see if we switch to inclusive, and we look at get value here, for example. So we're just getting the value from a reference. You can see we are looking into the global environment by calling global environment get binding value. Get binding value then does two things. It does has property and then also get. Time is almost evenly divided between the two. And that already seems like something that we don't need to do both of those things. Because, as you can see, both of them just kind of turn around and call the same function. So internal has property and internal get both end up calling internal get own property, which calls storage get, so on, which does an internal property lookup inside the global object. So it looks like object environment get binding value ends up first checking if we have the property, and then presumably if we have it, it asks for it. But there's probably exactly the same operation behind the scenes. So I think there is going to be our first potential optimization to just consolidate this operation. So that was get binding value. Let's see. Global environment get binding value, which calls object environment get binding value. Right. Yeah, so that's one thing to know about, by the way. The global environment is actually sort of a composite environment. So it has both a declarative environment and an object environment internally, because you can also have let things in the global scope. So if I do this, I think this is technically in the global environment, but it's part of its declarative environment rather than being a property of the global object. So at least I think so, right? So if I do global this.x, if I do that, it's undefined. Yeah, so if you use let in the global context, it does not become a property here. It ends up in the declarative sub-environment of the global environment. JavaScript. Anyway, so in our case, though, we're talking about a var, so that plumbs through down to this thing called the object environment. And there are actually two types of object environment in JavaScript. So global this is the one that you interact with the most because that's where all the global variables are. But if you use the with statement, so like with O, then most people probably never even seen this because it's just not popular anymore, but it's still a language feature. So if O were an object here that had a field foo, then you could you could just access that as if it were a global or a local or whatever. So let me see if I actually got that right. Yeah, prints out 1. And when you do this, this also creates an object environment. So this is the other type of object environment that we see, but it's very rare, whereas the global environment is constantly present. Anyway, that was just a little side note about JavaScript. So we were digging through global environment get binding value, calling down to object environment get binding value. So let's follow the trail of breadcrumbs here. So we're not interested in the declarative environment. We called through to object environment get binding value. And then we can see the first thing it does is just ask the binding object if it has a property with the name. So that was the thing we saw here, has property. So we find out if we have the property. If we don't, then either return undefined or throw, depending on strictness. Otherwise, we call get. So that get there is the second thing, which just does the same operation again. So it seems to me like we should be able to just do a single call here, at least if we're not strict. So what do I get from get? So the strict case is interesting because we have to throw unknown identifier if this property is not present. So what does get do normally? Get object get calls internal get. Okay, internal get gets the get own property. Okay, but if we don't have the property, then we try to get it from a prototype, and if we don't have a prototype, we return undefined. Oh, interesting. So actually, internal get can't really tell us that the property was not present because that state is indistinguishable from the undefined you get when the prototype is not there. So what does internal has property do? Okay, so has property does a get own property. If that succeeds, return true. Otherwise, check with the prototype chain. Okay, so the strictness thing I think is key here. So I guess we could add more metadata to this lookup thing so that the get function would like return additional information about whether the thing was actually present in the object or not. But I don't want to touch all of libjs and libweb right now, so I'm just going to do like a restricted optimization so that we only do this in non-strict mode. Because as you can see here in non-strict mode, if the value is not present, we just return undefined, which is exactly the same thing that get did. So if we say like this, if not strict, then just return binding object get name. Let's see if that works. Also, do I still have the test program looking? It's the same as I started with, yeah. Okay, so does that help? Yes, it does. So we are down from 0.88 to 0.74 already with that one tiny change. So that's pretty good. Although, let me just do a smoke test here. See that I didn't break tests. Okay, well, I didn't break our test suite. There's the whole test 262, but that takes a couple of minutes to run, so I'm not going to do that just yet. But I think this is sane. But we are deviating from exact spec algorithm here, so I am going to make a note of that. Like, I think we typically do something like optimization : yeah. So optimization. In non-strict, what's the, is there another name for non-strict mode? Sloppy mode. That's only used in 2 places, and maybe I'm the one who put that there, so I'm just going to call it non-strict because I'm not sure if sloppy is the right technical term for this. Anyway, in non-strict mode, We don't need the separate has property. Check. Since get will return undefined for missing properties anyway. So we take advantage of this to avoid doing both has property and get. Fix me. We could avoid has property. We could combine has property and get in all cases if get would return a bit more information about failure. A bit more failure information. Yeah, so that could be even better, but I think that's a good start. So we will commit that, lib.js. So avoid redundant has property. We'll check in object environment, or let's say make object environment binding lookup or binding get binding value faster in non-strict mode. Oh no, I can't fit non-strict mode. Well, can I fit sloppy? I can. So we're going with sloppy. All right. So what do we say about this? Actually, I mean, the comment here already explains what we're doing, so I think that's okay. Okay, so let's reprofile. I'll take another 0 off here again, and then Okay, let's take a look at the new state of things. So where are we now? Dun, dun, dun. We have get value is down here, 25%, and global environment get binding value now spends very little time, or much less time in, still does a has binding on the declarative environment. I guess we still have to, but in object environment, we only do a get. There's no has property and get. So that's where we saved all that time. So very, very good. Okay. So what about put value? So we made get value do less work. Are we so lucky that put value does stupid stuff too? Global environment set, object environment set, and set does a has property and a set. Bit less time spent in has property here, but can we avoid that as well, I wonder? Set mutable binding, is that the one? Wait, where did I want to go? Object environment set mutable binding. Yeah. So it calls has property and set. So set mutable binding. We'll check has property to see if we have the property before setting it. And then if we don't have it and we are in strict mode, then we throw some exception, sure. And then we call set. Sure. And then if some error occurred and we are in strict mode, do a bunch of stuff. Let's see, nothing like this is in the spec. This is here to produce nicer errors instead of the generic one. Okay, so this is just to make nicer errors in strict mode. And then if we have an error, return the error, otherwise return void, I guess. Yeah. Okay, so basically it seems to me like the same thing applies here. Probably, I think, because again, the interesting cases are only in strict mode. So what if we just say if not strict, then can we just do this? Like return, and we know that strict is false, and so it's not going to throw, so we can just hook that up right away. Will that work? Wouldn't it be nice if that just worked? Okay, so JS, test JS. That's too fast. I probably need to add the, add the 0 back. Bum, bum. Yes, okay. One more time. Okay, 0.707. So that is, again, a little improvement, actually. That's really, really cool. So we went from 0.74 down to 0.70 just from doing that. So I think that's probably completely safe to do that because this is just busy work. So we're checking if the property is there, and then only in strict mode do we even react to that. And then we go ahead and set. So outside of strict mode is totally, I think it's totally irrelevant. And I don't think that has property is not independently observable from the get. It shouldn't be. Or independently observable from get or set, as far as I know. So I think at least. Okay. So let's write a little note about that as well. Actually, I can maybe put that here. So we could, yeah, the same thing applies, I think. So in non-strict mode, we don't need the separate has property check since set. Well, actually here though, I have to describe it differently. Since we only use that information to throw errors, to errors in strict mode. And I think we could combine has property and set in all cases if set would return a bit more failure information. Yeah, because if set would tell you everything you need to know, then we could potentially do this in one swoop as well. But let's not get distracted with this big refactoring here. So let's say the same thing essentially, except this was set mutable binding. And now this doesn't fit. Dang it. Faster as well. Haha. Okay. All right, so now I guess we should grab another profile. And let me delete the old ones. Yeah, the zeros are a bit annoying, but Valgrind would take forever to churn through this test if we run a whole million times, and 100,000 times is plenty enough to get an interesting profile. Okay. So what else are we looking at here? Identifier execute. Identifier execute. Okay, so identifier is the AST node that you see. Not this one. This is a variable declaration, but this is an identifier. This is an identifier, and this is an identifier. And every time they execute, we do a lookup. And for let variables and function scope variables, identifier actually caches those lookups. But for global variables, we don't cache them. And that's probably something we can do, at least in some way. So what ends up happening here is that when we execute one of these identifier nodes, so it just says I, and we have to evaluate that. Like the easiest one to look at, I guess, is just to look at this one right here. This is a standalone identifier node. So when we execute that, we are here, and then we try to resolve the binding, the I binding. So we ask the VM like, hey, what's I in the context where I am currently executing? And that will give us back a reference, I think. And then we ask that reference for its value by calling getValue on it. And let's see. So what ends up happening here, get identifier reference, blah, 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 blah. So I think we can make this faster. So what we do for other variables like that are not global, let me, I think I made a video about that a long time ago, but I just want an editor. Can I get an editor? Where is my editor? Here it is. Okay. So what we do for variable, for cached variable access is that if you have a function like this, foo, and it has some variable inside of it, then this is not a global variable, right? It's scoped to this function, so it's part of that function's environment. And if you have nested functions like this, and you access x in here, so you say like return x plus 1 or whatever, then this x is this x. And the way that we find it is when you execute this identifier node, we have to traverse the environments on the stack. So we have this sort of capture stack of environments. So we go outwards. So we jump up to bar, look here. Do we have it here? Nope. Okay, we jump up to foo in this environment, and we do have an X. So we find it that way. And to make this fast, we only do this lookup the first time where we traverse the stack of environments. And then we remember how many times we had to jump or how many hops we had to make. And that we call that an environment coordinate. So we have this environment coordinate object, which has a hops and an index. And the index is basically, that's like a pointer into this environment here where we found it. So the first time that we resolve X here, we figure out that it's 1, 2 hops away. And since it's the only variable in this environment, it will have index 0, but it could have index 1, 2, 3, and so on. It's just a pointer into this environment. But if you are talking about a global variable, so something that exists out here, and you were to try to access that from in here, we will still like hop through these environments looking for G, but we're not going to find it. We won't find it until we try in the outermost environment, the global environment. But we don't have a way to express, oh, this was in the global environment. We don't have a way to say that with an environment coordinate. So we end up not caching these. So I think we just fail. If we look at identifier execute, when we resolve the binding, we do get identifier reference, which calls global environment has binding. Yeah, so we end up in global environment has binding. Has binding. Where are you? Here. And has binding is a virtual function in all environments, and it has this out parameter, but as you can see, we don't even use it in global environment because we haven't implemented any caching for globals. If we look at declarative environment, has binding, you'll see that we actually use this out parameter. That's the out index. And here is where we assign to it. So unless this environment is permanently screwed by eval, and out index is a non-null pointer, then we actually store the index into this out parameter. And then that's used by, I think by resolve binding or get identifier reference, or whoever calls this thing, interprets that as like, oh, this is actually a cacheable lookup. Just remember this index and you don't have to do the lookup next time. So all of that to say, I think we can maybe just do this. So global environment, like if we're doing a lookup, a binding lookup in the global environment, that will only happen like at the end of a lookup, because we will always traverse whatever function scope you're in, whatever block scope you're in, like all of those things will be checked first. Global environment is always the very last thing that gets checked. Because if something is not in the global environment and nowhere else, then there isn't any other place to look. So the fact that we're here means that for any future access, I think it's okay to look here again. And you can actually, maybe what we need is just to say this, if out index, and then some like magic number. So like this is a very big number, right? Like you're not going to have that many properties in, or not that many bindings in an environment. And yeah, I can't go larger because then I'll break on 32-bit. Yeah, we could do something nicer with this. Have like a magical constant or something. Let's do that. Environment coordinate, global marker, let's say. Okay, and here we will just say const expr global marker is what am I trying to say here? Static const expr, yeah. Okay, so yeah, so this is supposed to mean that we ended up in the global environment when looking for this binding. So in the future, you can skip over all of the declarative function environments and stuff like that, go directly to global for this thing. Yeah. That should be okay. And then, so let's see what happens if I try to just use this. going to break. So we have to teach reference how to actually make sense of these. So reference, let's look at get value first. So reference get value is called, and we have an environment coordinate cached. So for this memory for this reference, if we have an environment coordinate, then normally what we do is we just well, here we assume that it comes from a declarative environment, because until this point, only declarative environments actually produce environment coordinates. But in our case, so in that case, we would just call through and say like, hey, declarative environment, just give me the binding value directly given with a specific index. So it's like a sort of a hack that pokes through the layers and just grabs directly at a specific index inside of the declarative environment. But I think here, what if we just say environment coordinate index, it has to be not environment coordinate global marker. Yeah, and then it will not do this access, but instead it will do base environment get binding value. Wait, does this make sense? So if we find the variable, actually, like if we find it or not, it doesn't matter. The only thing that matters is that we know we have to look in the global environment. It can be there, it cannot be there, it doesn't matter in the global case, because it's kind of the fallback. So we can just fall through here, and this is going to be the global environment, because the reference will be pointing at the global environment in this case. I think this would just work. So then we can do the same thing for put. So reference put value, if environment coordinate and environment coordinate index is not environment coordinate global marker. So if it's not the global marker, then just go to the declarative environment, set direct with an index there. Otherwise, call base environment set mutable binding, which will call on the global environment. Okay, this is probably going to crash. It crashed. Okay. Too optimistic. So let's see where it crashes. It's crashing in identifier to reference. All right. Oh yeah. Okay, so here's actually the logic that I talked about, where we traverse the environment stack by n number of hops. So you see here we loop the number of hops and jump one environment out for every hop. This is how we do that. This is how the cached lookup actually works when this is the fast path or the happy path or whatever. And this is a bit harshly named, but very correct. The environment can be permanently screwed by eval, because eval makes the assumptions underlying this caching optimization, eval just breaks them. So whenever you do eval, we have to mark the environment as permanently screwed, and then we don't optimize anymore. But thankfully, people don't use eval very much, so that's okay. But of course, in our case, now we have an index of the global marker index. So I think we have to, wait, what are we gonna do here? Environment, if environment is this and that, I guess in our case, like if the index, if mcached environment coordinate index is environment coordinate global marker, then the environment is simply the interpreter VM current realm's global environment. Is that a reference? Yes, okay. Otherwise, we have to traverse. Let's see. Okay. Will that work? So if we, yeah, in the global marker case, we just go directly to the global environment. I need to put need to put the zeros back again. Ooh, 0.64. Okay, 0.63. Yeah, so that definitely helps. But did I break the world? May have broken the world. Nope. Okay, well that's good. Again, we have a lot more tests that we're gonna run also, but this is a very good smoke test here. The fact that I'm still running 1,577 test suites with over 4,000 tests total. So, and I guess I didn't need to do this here. I can do this here. So something like that. That's pretty good. Okay. So basically what we're doing now is that we're just caching the fact that we ended up in the global environment during a binding lookup. So the binding we're trying to access is not in any of the containing function environments or block scopes or whatever. We had to go to the global. So just remember that. And then in the future here, we know that, oh, we have to look in the global environment. And that's what we do here. We just create a reference into the global environment. And then we bypass the binding lookup. This is really nice. Okay. So let's commit this. libjs cache global environment cache environment global environment cache access to bindings in the global environment. This patch adds a special environment coordinate global marker value that signifies that a binding lookup ended up searching the global environment. It doesn't matter if we find it there or not. The global marker is always returned. This allows us to bypass other environments on subsequent access, going directly to the global environment. Yes, that's again a little bit faster, right? So we have gone down from where were we originally? Like 0.88, right? So now we are down from 0.88 to 0.64. Very nice. Let's see what else we can do. So again, let's get a little profile here. Again, I forget about the zeros. Maybe I should just make a separate file instead of editing this thing over and over. This is so stupid. Okay, let me just say test small JS, and test JS is the big one. All right, so test small. Okay, that's 720. Got it. All right, so what's going on now? We see get value, put value, identifier execute, identifier execute. Still doing a lot of resolve bindings. I would have expected those to go away. Why do you need to re-resolve the binding? Identifier execute. Oh, it calls resolve binding directly. But then identifier execute is just totally bypassing the optimization we have in identifier to reference, because that's where the optimization lives, to avoid resolve binding. So I think the thing to do here is to just do to reference. We'll have to add a comment about that, but if we do that, that should bypass the need to resolve. And we're down to 0.52. That is super nice. Shoot. Very cool. Okay, so did I break the world? I did not break the world. Okay, good. That's really, that's something we should have been doing all along, is not bypassing the optimization here. So I'll just make a note that this is optimization. We call identifier to reference here, which acts as a caching layer on around resolve binding. Yes. Libjs make identifier execute, use the actually use the cache. If we have cached environment coordinates for an identifier, we have to call to reference to actually make use of them. Okay, but that is excellent. So let's get rid of these. Let's get another profile. See where we're at. Okay. Get value, put value, blah, 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 blah. So what is the self time? Still a shape lookup, sure. But at least we've eliminated a whole bunch of redundant work. Update expression. So update expression is over half of the time spent. And it's calling get value and put value, which bottoms out in global environment get, global environment set. Sure. Yeah, so here is room for improvement for sure, because what we're looking at is basically this guy right here. This is the update expression. And the way that it's implemented is that it does a get, first gets the I, and then increments it by 1, and then puts the I back again. And that's what we see here. So update expression does a get, then the arithmetic in the middle, and then the put. And it should definitely be possible to come up with a way to cache metadata about this access, so that we don't have to do the lookup twice, or like do all of the grunt work, because once we find the location where this value is stored, we should like retain all the information we acquired in the get operation, use it to make the put operation fast, is what I'm trying to say. I think there's a ton of overlapping work between these two ops. Internal get, internal set. Both of them call internal get own property. Yeah. But this is a bigger architectural adventure, so I'm not going to get into that today. But I guess I'm pretty happy with how far we got already, and there's definitely room for improvement here. Like lots and lots of things that can do less. Many operations that do the same thing that can be consolidated or combined to atomic operation that does both, or that does everything in one go without repeating itself. But yeah, I'm already happy with the results. So before we go though, let me go ahead and run the libjs test262 thing, because I have a baseline that I recorded before starting the video recording. So it should be possible to build using just to rebuild the runner and then run and compare against this, because I didn't pull any other changes in the meantime. So it should be up to date. And then we'll see if we broke anything on test262, because then we have more work to do. But that's going to take a couple of minutes. So I guess we can, it'll take a moment to build here, and then we have to also run it, which will take a couple of minutes. So I guess we can also browse around in the profile in the meantime. Also, I really like this graph view that they have in KCacheGrind. It's super informative. It's nice to browse things around visually. I gotta make one of these graphs at some point for our profiling system. Of course, graphs like this are less reliable in an environment where you're doing a sampling profile like we do on Serenity. This is like a perfect instrumented graph, so you know that you see all the calls. I always forget the invocation because it's so long. Okay, here we go. Per JSON, per, what's the name? Per file. So what the first one was called baseline new.json. Let's call it that. Okay, and then this will run the 48,000 tests while I browse around here. Oh, actually, you know what? I'm just going to limit the concurrency so I don't absolutely murder the machine while I'm recording a video. Okay, so we'll let that work in the background. Yeah, update expression. We definitely need to find a way to make that faster. Get value. We're losing a little bit of time here in the declarative environment, because the global environment is this composite thing that has both declarative and object environment. But it's probably not a big deal. The object get, we could definitely make this even faster. Because right now, what we end up doing in reference, so when reference does a reference get value, if it's a global, then we go looking for it here. And if it's in the global object, we look it up by name. That's what we end up doing. But we could actually cache even more information about where exactly in the global object it is. Like, what is the exact property index in the global object? But we don't have a mechanism right now to cache that. But I think that would be a way to make this even faster, because then you could also just melt off the shape lookup here. So all of this stuff, this storage get stuff, you would instead just index into a vector, basically, if you knew the offset into the global object. Although, if you did that, that becomes a bit harder, because then if you delete a property in the global object, you have to invalidate anybody who's cached that property index. So that will require invalidation logic. But if you figure out how to make that invalidation logic, then you can make, you essentially end up making an inline cache. And that could be very, very, very fast. But invalidation is tricky. But you can figure out how to do that too. Like, you just have to have some kind of a indirect handle thing that you can invalidate, so that whenever you remove a property from the global object, you invalidate the handle. And then all of those caches can just double check with the handle before they reuse the cached value. Anyway, we're not going to do that today. So just thinking about potential improvements. 76%. I'm getting there. Identifier execute, still 33%. I mean, it makes sense that it's heavy because it is most of what we're doing. It's just looking at this I. And this is something, by the way, that's definitely able to get a lot faster in the bytecode VM. And I know that Leon has been working on some optimizations to eliminate redundant loads, I think. And that's going to be interesting for the bytecode VM, because then we can just eliminate these operations entirely, which we don't really have that kind of luxury in the AST interpreter, because we don't have a very clear picture of the program when we're just interpreting the AST. But in the bytecode VM, we have much greater liberty to optimize. So definitely looking forward to that. Okay, we are so close. 99, 100%. Okay, so I always forget. Per file result O, baseline. New. No errors. Ah, that's awesome. Okay. Didn't break anything, but we got faster. That is the best. So yeah, that's a really, really respectable speed up for however long this was, an hour or something. So from 0.88 to 0.52, I'll take it. So I guess this is where we're going to end for today. I got the low-hanging fruit out of the way, I feel like. Everything I see now is kind of mid or high-hanging fruit. So we'll leave those for another day. So if you made it this far, I thank you for watching, for hanging out. I hope that you saw something interesting here. And I'm certainly happy to improve performance of libjs a little bit. This was kind of limited to global variable access, but I'm sure that it's something that real world websites will do a lot of. So it's always good to make things faster. And I'm pretty happy with the sort of limited intrusiveness of the optimizations that we did. I feel like they were all pretty justifiable. Anyways, thank you for watching, and see you all next time. Bye.